Oh no. My webcam once again is not working. Let me fix that. Oh, so much better. Okay. If we just go ahead and do this, and then move this over here, we should be good. It's unclear to me why this changed from last time, but that's okay. Hope everyone's having a good night. We're about to do day 23 of Advent of Code, which means it is the evening of December 22nd for me. Let me go ahead and take off this sweatshirt real quick. I'm sure that I will want it a little later, but for right now, I'd rather have my forearms free. For some reason, that makes a difference when I code. I'm not exactly sure why. If we check out the leaderboard and look at the personal stats, yesterday we got 616 on part 1 and 176 on part 2, so pretty good. And for the private leaderboards, yeah, obviously nobody's done anything here. Everybody gave up a long time ago. And on this other one, Kevin Chung did in fact get the first part of yesterday's, so he's the only person that's kept up over the course of about the past week, but that is unsurprising. At the end of the year, it's a hard time for a lot of people. People get very busy. But you know, that'll happen. No biggie. I'm curious whether or not today's is going to be really hard or really easy. I feel like when you get close to the end, some of the problems are really rough. Like yesterday's was pretty rough. If we look at, we still have 3 minutes, so we got plenty of time to look at this. If we look at this, I got 176 with an hour and 24 minutes worth of work. So that's pretty long. But if we look, let's see. Yeah, these are all under half an hour. Then one that took us 50 minutes, but that's because we sucked at the first part. We were just terrible on that day. And then still everything's under an hour, and then things start to get harder here. In fact, we probably would have a better time figuring out what's going on if we, first of all, if we move this a little over. But then also if we look at the stats, we can see, okay, you know, all these days are just sort of a steady decline. There's a big drop on day 7, which took us a little while. That's fair. Day 8 comes back. And then a drop here, kind of a steady decline. Another big drop on day 16. Apparently day 18 was easy enough that people came back. And then another big drop from day 21 to day 22, which is not that surprising. It's a Wednesday. Yeah, day 22 in particular was really tedious with that cube. We still, if we look at the full screen and we take a look at the whiteboard over here, we still have the cube up on there. So that's great. Oh, great. And now we're too low. That's okay. We're just filling the time right now while we wait for things to begin. There we go. Yeah, I got about 1 minute and 36 seconds left. Yeah, it's also very interesting to see what the ratio between these two numbers is. Like, everybody got both parts of day 1, but like only just over half of people did part 2 yesterday. You see like a 3-to-1 ratio here, like a 5-to-1 ratio here, versus this is like a 23-to-1, and this is like a 20-to-1. Huh. I guess that does kind of tell you the problems that really have optimization holes, you know, places where you really need to optimize in order for stuff to work. It's also interesting. I finally figured out I got a bunch of users in my Twitch chat, and I was like, who are these people and why are they there? And it's just a bunch of bot accounts that have decided to follow and sort of show up in chat. So they're not viewers, they're just bots. But it's interesting that like my chat room is polluted with so many of these bots, and then it's the same bots for everybody. I wonder what those bots do. It's unclear to me, and why they aren't named things that make it clearer that it's a bot. I have so many questions now that I think about it. It'd be nice to get some answers. Well, in the last remaining 27 seconds, I'm going to try and attempt to plug in my headphones here so that I'll have those ready. Today was a chemo day for Mel, so she's upstairs asleep already. She's been asleep for a while. Yeah. Okay. Here we go. 3 more days. And let's get this one ready. 2, 1, let's go. Day 23, Unstable Diffusion. You enter a large crater of gray dirt where the grove is supposed to be. All around you, plants you imagine were expected to be full of fruit are instead withered and broken. A large group of elves has formed in the middle of the grove. But this volcano has been dormant for months. Without ash, the fruit can't grow. You look up to see a massive snow-capped mountain towering above you. It's not like there are other active volcanoes here. We've looked everywhere, but our scanners show active magna flows. Clearly it's going somewhere. They finally notice you at the edge of the grove. Your pack almost overflowing from the random starfruit you've been collecting. Behind you, elephants and monkeys explore the grove, looking concerned. Then, the elves recognize the ash cloud slowly spreading above your recent detour. Did you just... Before any of them can form a complete question, another elf speaks up. Okay, new plan. We have almost enough fruit already, and the ash from the plume should spread here eventually. If we can quickly plant new seedlings now, we can still make it to the extraction point. Spread out. The elves each reach into their pack and pull out a tiny plant. The plants rely on important nutrients from the ash, so they can't be planted too close together. There isn't enough time to let elves figure out where to plant the seedlings themselves. You quickly scan the grove, your puzzle input, and note their positions. For example, ... hash ... etc. The scan shows elves, hashes, and the ground. ... Outside your scan, more empty ground extends a long way in every direction. The scan is oriented so that north is up, orthogonal directions are written north, south, west, and east, while diagonal directions are written northeast, northwest, southeast, southwest. The elves follow a time-consuming process to figure out where they should each go. You can speed up this process considerably. The process consists of some number of rounds during which elves alternate between considering where to move and actually moving. During the first half of each round, each elf considers the 8 positions adjacent to themselves. If no other elves are in one of those 8 positions, the elf does not do anything during this round. Otherwise, the elf looks in each of the 4 directions of the following order and proposes moving 1 step in the first valid direction. There's no elf in the north, northeast, or northwest. The elf proposes moving north 1 step. If there's no elf in the south, southeast, or southwest positions, the elf proposes moving south 1 step. There's no elf in the west, northwest, or southwest adjacent positions. The elf proposes moving west 1 step. Otherwise, east 1 step. In that order. After each elf has chosen has a chance to propose a move, the second half of the round can begin. Simultaneously, each elf moves to their proposed destination tile if they were the only elf to propose moving to that position. If 2 or more elves propose moving to the same position, none of those elves move. Finally, at the end of the round, the first direction the elves considered is moved to the end of the list of directions. For example, during the second rounds, elves would try proposing a move to the south first, then the west, then the east, then the north. On the third round, west, then east, then north, then south. Got it. As a smaller example, consider these just these 5 elves. The northernmost 2 elves and southernmost 2 elves all propose moving north, while the middle elf cannot move north and proposes moving south. The middle elf proposes the same direction as the southwest elf, so neither of them move, but the other 3 do. Next, the northern 2-most elves and the southernmost elf all propose moving south. Of the remaining middle 2 elves, the west one cannot move south and proposes moving west, while the east one cannot move south or west and proposes moving east. All 5 elves succeed in moving their proposed positions. Finally, the southernmost 2 elves choose not to move at all. Of the remaining 3 elves, the west one proposes moving west, the east one proposes moving east, and the middle one proposes moving north. All 3 succeed in moving. At this point, no elves need to move, so the process ends. The larger example above proceeds as follows. Initial state, end of round 1, end of round 2, end of round 3, 4, 5, end of round... There's 10. To make sure they're on the right track, the elves like to check after round 10 that they're making good progress towards covering enough ground. To do this, count the number of empty ground tiles contained by the smallest rectangle that contains every elf. The edges of the rectangle should be aligned in the north, south, east, west directions. The elves do not have to have the patience to calculate arbitrary rectangles. In the above example, that rectangle is this. In this region, the number of empty ground tiles is 110. Simulate the elves process and find the smallest rectangle that contains the elves after 10 rounds. How many empty ground tiles does that round contain? Let's go here. Okay, so we got a big thing. Okay, cool. So I'm already thinking that I don't really want to store a grid because that grid's probably gonna get like huge. Like if we look here, 5 elves end up taking up a 5x5 grid. And so we probably got, how long is this and how deep is this? Let's take this and put it in the data so we can see. It's 70 by 70. Okay, so maybe half of those are elves. So 4,900, 2,500. We could do a 2,500 square thing. Yeah, so if we make a grid of size about 10,000, we should be okay. And then we just need to place this stuff in the middle of them. So we'll increase the X and Y values by a considerable margin. So first of all, what do I want? Boolean. Grid equals new Boolean. And let's throw... We have an alternative thing that we can try where we just store all of the points but don't really store a grid, and then we store all the elves' positions in a hash map and remove and insert them, which we can certainly do. But it's very... Is that better than doing 100 million points for every round? Let's try that approach. I'm gonna mess with the grid approach rate later, and we'll just comment this out: private static final int grid size equals 10,000. Cool. So what I want is I want a static class point int x int y point int x int y this dot x equals x, this dot y equals y. So those points are fine, and yeah, so we can basically just have a set of points. Then we can do some stuff based on that. Okay, let's try reading it in. We'll figure out whether or not we need to do something else weird. Int which row equals 0. String line equals scanner dot next line. For int which column equals 0. We'll say in this column num actually. Row num? Is that right? No, let's stick to what we had before. Which row? Which column? Which column less than line dot length plus which column? Then I want, let's start with a list and see if we need to use a different data structure. A list point elf locations equals new array list, and this is going to be, it's called about 5,000. In fact, let's go to about 2,500. That's probably better. Let's not mess with the initial capacity. It figures itself out better, probably. And we need to remember plus which row, which column. If line dot care at which column is a hash. Elf locations dot add new point, and its x is going to be which column, and its y is going to be which row. Okay. Cool. So that's all the elves. So now for this, I want for I equals 0. For int I equals 0, I is less than 10, plus I. Simulate round. And I want to give it elf locations, and then I want to give it I %4. Okay, so now we can write simulate round, private static void simulate round takes in a list of point elf locations. It also takes in an int direction order. Cool. So for each elf, we want to check the directions in order. I'm trying to think of the best way to do that, because we're doing the same thing. We're just doing a different So for each elf, I want to figure out which direction I would move if I would move in any direction. So let's look at this again. Blah blah blah. If there are no other elves in one of the 8 positions, the elf does not do anything during this round. Cool. So that's the first thing we want to check is yeah, screw it. I actually want this class to be elf. Elf has XY. I want a Boolean is anyone next to me. And I want it to take a list elf locations. So I want return elf locations dot contains oh, I need like an equals. Cool. Yeah, override public boolean equals. Not what I want to do. So let's look up overriding equals, which we've done several times. Java override object equals. Blah blah. So let's pick the object O because that's always nice. If not O instance of elf, which we don't really have to worry about. Fine, return false. Otherwise we can say elf other elf equals elf O. Return this dot x equals o dot x and this dot y equals o dot y. Crap, and this needs to go in here. Sorry, not O. Should be other elf. That should make you happier. Much better. Much better, much better, much better. Okay, elf dot contains new elf. Let's see. We want to check every direction, so we want x minus 1, y minus 1. Is anyone next to me? So or there's 3, 4, 5, 6, 7, 8. And that should do it. So x minus 1, y, x minus 1, y plus 1. Should do x, y minus 1. Should do x, y plus 1. Should do x plus 1, y minus 1. We should do x plus 1, y. And we should do x plus 1, y plus 1. That should go a little better. Cool. So is anyone next to me is just going to return, hey, do you have any of these things? Which this might be like a slow and dumb way to do this. If we were using an actual grid, that would be better. But that's okay. I think that the queryability of this might be nice later, and mostly it saves us not having to deal with negative numbers. Okay, so now simulate round for elf current elf in elf locations. So now I want like a list elf proposed elf locations equals new array list of size elf locations dot size probably. So if is current elf dot is anyone next to me elf locations. Otherwise we skip. Switch direction order. Case 0. Actually, we can. Let's just put proposed elf locations dot add current elf dot get next location direction order. Get next proposed location. So now I want elf get next proposed location int direction order. And then I want elf get north location or null. And then I want the same for, what is it? North, south, west, east. South location or null. West location or null. East location or null. Fantastic. Cool. Let's make all these return null right now. We'll fix them in a second. Because all these are going to do basically the same thing. And all of these need to take in list elf locations. Yes, I know. Okay, so now I want switch direction order case 0. Let's just copy this. 3, 2, 1. Cool. So this is gonna go. This is north, south, west, east. It's weird that there's north, south, west, east, and not south, west, east, north. West, east, east, north, south, and then east, north, north, south, west. So for this, I want to next location equal null. Equals get north location or null. This also needs to take in a list of elf locations. So let's do this. We just forward that on down. If next location not equal null, return next location. Then we just want to do this same thing. So and I'm going to do something kind of weird. Int count equals 0. Plus count. We're just going to go ahead and go here. I want to copy this same thing into the 4 places. And then after we get outside these cases, then what I'm going to do, so I just want elf next location equals null. There we go. Now we can just remove the elf statement here. Then we should be good. Excellent. Just remove the spaces on the ++ count because that's gross. If count is less than 4, and then I want to do north now. I basically want to do the same thing. 1, 2, 3 times. For the next one is get south location or null. get west location or null, get east location or null, north, get south, get west. Cool. So that should do it all. Basically, like it's just going to start at the correct one and then continue its way through. Then after we've tried all these, just return null. Like there's nowhere you can go. Great. Get next proposed location. Cool. So now that we have that, except we don't want to. Yeah, so we need elf locations and direction order. Elf. Next location equals current elf dot get next proposed location, which is fine. Then we want to add that to the thing. So if next location not equal null, and then we're going to want to like strip this list. Next location. Great. It's cool. So now we've got all the proposed locations. Now I want to like sort. So I need like a compare. At override. Right, implement methods. I want like comparable. No, we can just make a custom comparator for elves in the method. So we want to sort them by. So now what I want is proposed elf locations dot sort new comparator elf return. Let's see. Let's go. O1 dot x minus O2 dot x times I don't know plus O2 dot or O1 dot y minus O2 dot y. Cool. So it's gonna bias x over y. Everything's it should play all right. So basically, if we're to the left of or if we're above the other one, we should be good to go. And it's gonna kind of go in like a row order. And 10,000 should be big enough. Okay, so now that we've done that, for int I equals 0, I is less than proposed elf locations dot size minus 1 plus I. If proposed elf locations dot get I dot equals proposed elf locations dot get I plus 1. Then I want proposed elf locations. I actually want wow. This happens. Dot remove. And I want I plus 1. And does remove object remove all instances of that object? Remove. Removes the first occurrence of the specified element from the list. If it is present, if this list does not contain an element, it is unchanged. More formally, removes the element with the lowest index such that object that equals code, blah, blah, blah. Okay, cool. So that's only going to do it once. So first we want an if check here, and then we want, yeah. If this is true, then please start removing all of these, and then proposed elf locations dot remove I, and then we want to go minus I, right? So that it'll start again at the thing, and then this should be computing size every time, so that should go fine. Crap! But then how are we gonna remove the right? Geez. How are we going to figure out which old elves to remove? Crap. Okay, so I'm gonna make another class that's gonna help us do this. Static class proposed elf location. It's going to have an elf old location. It's going to have an elf new location. Proposed elf location, elf old location, elf new location. This dot old location equals old location. This dot new location equals new location. Cool. So now I want each of these to instead return a proposed elf location. I'm going to do this for all these things. And then I want this to return a proposed elf location. We still have to implement these. Okay, let's get north or null. If not elf locations dot contains new elf, what is it? So this is what, x, y minus 1, and nope, there we go. Should be x minus 1 minus 1, x plus 1, y minus 1. Then it's none of the places. Let's get rid of this ampersand. Then we want to return new proposed elf location. This new elf x, y minus 1. We can basically copy this, and we're just going to change a couple of the things inside. So south is this, but all the y minus 1s are now y plus 1s. West is everything is x minus 1 here. And then this should be, yeah, y minus 1 is fine. Y plus 1 is cool. And then it's going to be x minus 1 y. And then we can just do this same thing. Let's get rid of the empty line there. But we can just go x plus 1, x plus 1, x plus 1. We're going to have to do some weird type wizardry here. Okay. This is going to be creating and destroying a lot of objects, which is kind of dumb, but fine. So this is going to return a proposed elf location, get next proposed location, proposed elf location. And proposed elf location is going to be proposed elf location. Fantastic. And let's, whoop, escape. Let's do that. So now this needs to have a new comparator proposed elf location, which is this and this. 01 dot new location dot x. So let's just take this and put it after every period. Fantastic. That should still be fine. Then what we want to do is, after we got all these, so now after all the proposed locations, and the proposed location needs an equals, I suppose. Let's override that equals, and we can just have it equals based upon the new location. So where's our overridden equals this? I'm gonna put that here, and then we're gonna say proposed elf location. Otherwise, we can just go like this. And now we can say this dot new location dot x. So we need to put this after each of the things, and this dot new location y equals this. Cool. So now if they equal dot equals this, then we want to remove that, then we want to remove itself, and then we want to go through. So now we've got all distinct locations. So now for proposed elf location in proposed elf locations, we want to elf locations dot remove proposed elf location dot old location, elf locations dot add proposed elf location dot new location. And that should pretty much do it until we've done all this stuff, and then we just return, right? And in fact, I'm gonna have this return an int. And what I want to do is I want to return proposed elf locations dot size. It's just going to tell us how many elves move. I can guarantee you that that's something we're going to care about later. So once we've got all of these, now I need another thing, which is private static int size of bounding box. And we're actually going to make this all long. Just in case it gets huge, because that's what it's asking for, right? In this region, the number of empty ground tiles is this. Okay. Which we can get just by finding the size of the box and then subtracting the number of elves. Number of empty ground tiles. No, this shouldn't be that big. Let's keep it an int. We'll make it a long later if we need to. And this is an elf list. Elf locations. Okay, so I want what's gonna make the bounding box here? It's like the minimum x and the maximum x and the minimum y and the maximum y, right? So int min x equals integer dot max value int min y equals same thing actually. Int max x equals integer dot min value int max y equals integer dot min value. Just make sure we get the right things for elf in elf locations. If min x less than elf dot x, min x equals elf dot x. We can do the same thing basically 4 times. Min y less than elf dot y. Whoa, except this is if min x is greater than. If min y is greater than elf dot y, min y equals this. If max x is less than elf dot x, then max x is going to do this. And if max y is less than elf dot y, y, escape. Max y, cool. Return, and I want max x minus min x times max y minus min y minus elf locations dot size. That should do it. So then what I want to print out is number of empty ground tiles plus number of empty ground tiles elf locations. Fantastic. Let's put in our little example up here and see what we can do. So go ahead and run. Okay, index out of bound 7 for whatever, for simulate round here. While I is less than proposed elf locations dot size and -1 and all of that stuff. And let's get rid of this line break. Okay, line's a little long, that's okay. Run again. Is 88, which is not right. Let's see. A larger example above proceeds. Okay, so let's try it and see what we get. In fact, it uses this size of grid, and the size of the grid doesn't actually change anything. So let's just go ahead and do that same thing, but it's going to make debugging easier. And then I basically want to debug simulate round. Cool. So if we look at elf locations, it's 22, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Perfect. So let's look at elf locations dot contains what is it, 0, 1, 2, 1, 2, 3, 4, 5, 6, 7. New elf 2, 7? Should be 7, 2 actually. Great. What about 8? Sorry. 5, 3? Yeah, seems good. So let's run it again. And now these 22 things. So this one. So now we want to see that there's one at elf locations dot contains new elf. And it looks like there's something at 1. And it's 0, 1, 2, 3, 4, 5, 6, 7. So 7, 1. True. And then 5, 2. Is that right? 5, 2. And then this other one is 6, 7, 8, 9, 9, 2. 9, 2 is true. 3, 3. Is that the next one? 3, 3. Okay, in fact, let me get a little thing here. I want to be able to print it out. Private static void print out all elf locations. List elf locations. So int min x equals 0. Int max x equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We'll just use the int min y equals 0. Int max y equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. To do adjust bounds based on input for int x equals, actually it's int y equals 0. Y is less than max y. This should be min y. Plus plus y. Yeah, and so we're going row by row, which is down the y, or int x equals min x. X is less than max x. In fact, you need to make this 14 and 12 then. No, let's do this and we'll just go less than or equal to. Be plus plus x. If elf locations dot contains new elf x comma y, system dot out dot print hash else system dot out dot print dot, and then we want system dot out dot println. And then at the end of this we want to put out another one. So for each of these I want to do print out all elf locations system dot out dot println elf locations plus I rounds. Cool. So now let's try running this and see what we get. Stop and rerun. And let's compare. So this does look like that. This does look like that. This does look like that. And let's see, let's look at 10 rounds and see if it's the same. Sure, 9 rounds. And then we want to put this down afterwards. Elf locations after 10 rounds, and then print it all out. So do the same thing for me. Show me it after 10 rounds. It looks like we're simulating correctly, so we must have something wrong in our like bounding box. Cool. So let's go to a number of empty ground tiles and try and figure out what's going on here. Debug. Don't care about this. Please move forward. What are we upset about? Why are we complaining about the variable grid? There's nothing. Remove that watch. Fantastic. Take me to this. So go through all of the things. Go until you get to here. The next is 1. Does that look right? Yeah, min x is 1. Max x is whatever this is. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's right. So 1 to 12 is 11 spots? Or is that right? Or oh no. Next minus this plus 1. This also needs a plus 1. Okay, cool. Now if we run this, do we get the right answer? It should be pretty straightforward. 110. Okay, cool. Let's wrap. Okay, let's take these and we'll comment them out and we can wrap them in an if debug later. So now if we take this and we instead run that in, 3684. Let's see if that's right. It's the right answer. I got 927. Continue to part 2. It seems you're on the right track. Finish simulating the process and figure out where the elves need to go. How many rounds did you save them? In the above example, the first round where no elves move was round 20. Figure out where the elves need to go. What is the first round where no elf moves? Cool. So this is actually going to be relatively easy. Let's go here. We knew this was coming. So let's take this and let's paste it into part 2. And now instead of for I equals 1 to 10, we're just going to say int which round equals 0. While true, int num elves moved equals simulate round, which round percent for, plus which round, which this is end of round. If in fact we want to get our, we might have an off by 1 condition, so we're going to put this before. Can't tell if somebody's knocking on my door or not. It's always a little tough because when people open doors, it rattles my door. If num elf moves equals 0. Break. First round with no movement, and that's just going to be which round? Let's go here. Let's call part 2. Let's run it. Is 20. Fantastic. Take this. And, whoop, nope, don't debug it, just run it. let's stop and then let's add a little thing just so we can see what's going on. If which round percent 100 is 0, if debug and this system.out.println on round plus which round. Private, oh geez, whatever I just did, don't do that. Private static final boolean debug equals true. Run it. Stop and rerun. Okay, so it's going all right. And if we take a look, CPU usage is reasonable. I mean, we're streaming to the internet right now, so that's unsurprising. Yeah, Streamlabs is using some GPU. Nothing else really matters. Yeah, all right, 600, cool. So as long as we can watch this go up, it's fine. And we expect, it took 20 rounds for how many else was this? 22? So if this is like 2,500, we expect to take 2,500 rounds, which is gonna come up any second here. And a lot of the trouble we're having is probably related to just the thrashing of creating a bunch of stuff. 862, let's see if that's right. That's the right answer. 850 on the stars leaderboard, completed day 23. So 10 minutes would have won us the day. And we completed the whole thing in like 47 minutes. So 21 minutes for part 2. That's the first star. So 21 minutes. And then yeah, first guy did both parts in 10 minutes. And it took us 47. Yeah, it's not terrible. So it took us about twice as long as it took the first 100 people, which is, again, not bad. So look at our personal stats, 927, 850. That's, again, we wrote expecting to have to retrofit. And if we look at the private leaderboards, nobody has done today. Fantastic. Okay. Well, let's go back, and that's, I'm going to clean up the code a little bit before I do anything else. And namely what I'm going to do is I'm going to just wrap these in an if debug to make life a little bit prettier. And then we can undo this. Then we can say tab, tab, fantastic. If debug, let's do this. There we go. And then we basically just want to do the same thing in the other two places that are commented out here. Which is great. And then everything else, need to test prod data. Cool. Okay, so now let's go back and add the write-up. Unstable diffusion. Got both stars as the end of this problem statement. And now we just do our nice little chill, sit here and fix it things. Let's add a line here. And get rid of the project statement for now. This matters. Going somewhere. Random star fruit that you picked up. How big is blah, 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 blah. For example, yeah, there's nothing else going on. Alter this. Ground is that. Outside your scan extends a long way. Scan is oriented so that north is up. Surprise, surprise. North, south, east, and west. You can speed up this process. Processing considers a number of rounds. During the first half of every round. The alpha does not do anything. Otherwise, the alpha looks in each direction and proposes moving in the first valid direction. We're going to get a few nice little markup language stuff here. Enter and delete, and then north. Oh, nope, undo. North, south, west, east. The second half of the round. None of those else move. The first direction the elves consider moving is the end of the list. Consider these here. And we're gonna add some new lines because it makes me feel nicer about the diagram. Northernmost. This, so we're good. There's still no bolds. Not what I want. Okay. And finally, at this point, no elves. The southernmost two elves. Okay, at this point, no elves means move, so it proceeds. Larger example. Oh, and this just goes all the way down, which is nice because I don't have to mess with the formatting. It's after round 5. Do a few more rounds. To round 10. To make sure the right rectangle is. Region and ground tiles is. Oh, we have to bold and then make code. And we can just go over until we see how, and then bold this whole line. Your answer was this, what is correct? Part 2. So you're on the right track. The first round where no elf moved was round 20. Which is cool that they printed it out. That doesn't really matter to me. This is the first number of rounds where no elf moves. Answer is this. Puzzles are complete. Fantastic. Okay, let me explain what's going on here real quick. So the elves start standing in a grid where every hash mark is a grid, and basically they have this process of figuring out whether or not they can move, where if no one's around them, they don't move because then they're good. And otherwise what they do is they like try and go up, then they try and go down, then they try and go left, they try and go right. And anytime that they like find a stable direction, they like propose a move. Now if 2 elves move so that they would be standing in the same square, neither of those elves moves. So what we did is first we just read in all the locations, and you could model this as a grid, but the elves are constantly going to be like expanding out. So you have to figure out how big to make the grid, and then you have to like copy the grid a bunch of times in order to like figure out what proposed moves are and stuff. So that's a thing where I didn't really want to have to deal with that. So instead I just stored all the locations in a list, which is fine. And I basically just said for the input, you know, keep track of the column and the row and use that to create an elf, which is just a class which stores a point and then has some helper functions. Then what I do is I simulate a round. So given the direction order, which is 0, 1, 2, 3, because it's where is it? Simulate round. Back up here. We simulate a round, and that's basically it determines the orders in which the elves check. They go north, south, west, east, and then they go south, west, east, north, and then they go west, east, north, south, and then they go east, north, south, west. And so that determines how that works. So simulate round for each elf. It basically, we have a proposed elf locations, and that's a class which holds an old location and a new location, which we'll explain why we need in a moment. We check, first of all, if no one's next to the elf, then they don't have a new proposed location. Otherwise, we say, hey, give me your new proposed location, which there might be no proposed location that works for the elf. It might be just completely surrounded. But if that's not null, then we add it to the proposed elf locations, which again is a class which holds an old elf and a new elf. Then we sort those, and then we take that list and we remove all duplicates, like all duplicates. So we go through, and if this one, because we sorted it, it's fine. We take the first one, and if it's equal to the second one for any I, then what we do is we just keep removing the second one until they're not equal, and then we remove the first one, and then we like go backwards one so that we're still iterating through the list correctly. And then for each proposed location, we removed that elf's old location and then add that elf's new location to the list of locations. And then we return how many elves moved, which is the size of the number of proposed elf locations that ended up working out. So yeah, once we do that, all we had to do was simulate the round 10 times in part 1. And then we just need to find the number of empty ground tiles, which is just the bounding square of elves on the XY axis, which is just the minimum X location owned, the maximum X location, the minimum Y location, the maximum Y location. And then we just multiply those to get the area of the full grid. And then we just subtract the number of the elves, which is pretty trivial. So part number 1, not so bad. Part number 2 just says keep simulating until none of the elves are moving and tell me which round that happens in. So simulate round, you'll notice, returns the number of proposed elf locations that still existed at the end, which is the number of elves that actually moved. So we just have to wait for that to turn 0, and we just count until that turns 0, and then we're good. We have a little debug statement so that we know how long we're waiting. And it ends up taking, I don't know, 20, 30 seconds, so it's not a big deal. And then we print out that first round, and we have some off by 1 stuff that happens. Basically, you start on round 0, but then when the first round happens, now the round that you need to be returning is 1. So we do this before we make the check to break out, which is fine. So that's pretty much all there is today. You'll notice that there's a little bit of like the elf. What up, Jay Gambles? You'll notice that the elf location, like that needs to get checked, is north, south, west, east. But then it just keeps going north, south, west, and it basically checks until you've tried 4 locations. So that's pretty much all there is. And then each elf like itself can tell you whether or not it can go to either of those directions, and it can also tell you whether or not it's next to anybody. And proposed elf location basically just has a pretty naive equals function, and just holds 2 locations. So it's I'm not super proud of the class structure, but this made solving the problem pretty easy. And again, pretty happy with the result that we got, which is 927 and 850. And given that we expect about 15,000 people to solve this, and usually somewhere between 3,000 and 4,000 people to solve it in the first night. In fact, if we even go with the stats right now, already 1,100 people have solved. So the fact that we're in the top 1,000, I feel pretty good about. I think that's all I got for you guys tonight. I'm kind of sad that there's only 2 days left. I was pretty pleased, though, that this one was not like a super stamina exhausting one like some of the other like 3-hour long solves were. So I'm going to take advantage of the fact that it is... I spent a sub-hour solve, and good night to you, Jay Gambles. Hope you have a good one. All right, peace, folks.